All right, let's begin. Let's get your notes out. Here we go. So, tan graphs. Tan graphs is considerably much easier than sine and cosine. I draw tan graphs just so easily because there's only one x-intercept that you got to find, and then you find the rest. So, this is how it works. Now, I know there are these formulas that make students feel like it's too hard or whatever it is. You can follow it if you want. I don't. I just simply find the first asymptote and I figure out the rest, right? So you can use this formula, which makes it look scary. And you can use this x-axis intercept if you want as well. I don't. That's why I don't get nervous by those formulas, or I don't feel like I have to remember them. I just simply do it logically. That's how I do it. Okay? So, what are these points? There are a couple of things that makes a tan graph different. So let's start off in your notes. You should have y is equal to, again, a is the dilation, multiplied to tan of, again, I'm going to put n as my dilation, times x. Okay? Now, a tan graph, I want you to think about the unit circle again. Tan graph talks about the gradient. The gradient as you move around the circle. So starting at this point, this is 1, 0 at that point. The angle 0 degrees. The gradient is 0. The green line that I'm drawing right now, that is the gradient. That's the line to make 0. So it's currently sitting like this. So tan graph, tan of 0 degrees is currently 0. Okay? Tan, when I move up, I don't know what the gradient is. At the moment, I don't know what that value is, but I do know one thing. The gradient, that line, is a positive gradient. Okay, it's not a negative gradient. So remember in year 9, you learned 4 types of gradients in general. This is 0, that's positive, that's negative gradient, and then you had undefined gradient. Those are the 4 types of gradients that you had. So I'm going to draw on the screen so those who are watching will remember. You have 4 types of gradients. You have positive gradient, negative gradient, 0 gradient, and undefined gradient. And all of those come from rise over run. So if you take a number divided by the bottom number, that's what you get. Rise, positive, divided by, let's say, left or right. You get plus or minus, hence positive gradient, negative gradient. 0 if you get 0 divided by anything, and undefined comes from the fact that the denominator is 0. Okay, so how does this change things? A tan graph, one of the things that we noticed just now, there is an undefined gradient, which means that if you're going to find tan of a particular angle, at some point in the graph, you don't have an answer. If it doesn't have an answer, it means it's going to be undefined. If it's undefined, it means you can't put a coordinate there. So it's what we call an asymptote, kind of similar to what you learned with exponentials and logs. So tan graphs is different to cosine and sine because it has an asymptote. Now, not only that, let's have a look at what's happening in the gradient between 0 degrees to 90 degrees. This is 90, this is 0 degrees. If I zoom in and we're going to draw multiple lines just to look at what's happening to the gradient. Okay, up until I get to 90. This is 90. You start off at 0. I told you I didn't know what the gradient was, but I did know it was positive. What's the difference between this positive gradient and this positive gradient here? As I'm moving around, what's happening to the gradient?
It's getting higher.
It's getting higher. So tan of the angle, as you increase the angle, the gradient is also getting larger and larger and larger and larger and larger and larger. The question is, how large? Now this is where you notice that by the time you get to 90 degrees, we don't have an answer. It's a vertical, undefined line, but what if it was just slightly off? Instead of 90 degrees, what if it was 89.999999 degrees? What is the gradient at that point?
You're very close to infinity.
Yes, be very close to infinity, a very large one. So what you can expect is the gradient of this at before 90 degrees, it must be infinitely large. The gradient value has to be so large. But then what's interesting is right after you get past 90 and you get into, say, 91 degrees, what type of gradient is this now? Negative. But what's happening with the negative? As I'm moving across, what's happening to the negative? It decreases, or technically increases, getting closer to 0, isn't it? So that means it started off at 91 degrees. It must be a very, very, very large negative gradient. Okay, so you can see, as I give you the graph now, I'm going to draw a tan graph for you to see. This is what a typical tan graph looks like. Tan graphs, we knew that from 0 degrees to pi on 2, which is 90 degrees I should have undefined line. As I'm getting towards that graph, the graph should reach an infinitely large, right? We said that after 90 degrees, which is 91 degrees, which is over here, we said it's infinitely negative. As I continue closer and closer, so as I keep moving, it gets smaller and smaller, getting closer to 0 until it reaches 180 degrees, which is at pi. It should reach 0. So this is what the graph would look like, infinitely close to pi on 2. And by the time it gets to pi, this is what the graph looks like. So technically, that's one cycle. But your textbooks will not draw it like this. This is from 0 to pi. But notice, how long did it take to get back to the same point again before the graph continues on with the same pattern? It only took a distance of pi. This is different to sine and cosine because remember, sine and cosine took 2 pi to make the same one cycle. So if you remember the sine graph, it went up, down, and then it repeats again, and then it repeats again. That took 2 pi to get there for that cycle to repeat. Whereas in tan, we can already see that the cycle will already continue as soon as pi hits, you now repeat the cycle. So the difference already, in your notes, you can see here, they say the period formula is pi on n, not 2 pi on n, because tan graphs have a cycle of only pi and not 2 pi. And the over n is simply the dilation factor. Okay, so when I'm answering this question here, I want you to note that the textbook will not draw this as your graph. It looks too separated. This is how they normally draw it. They say, well, since this is only a distance of pi, that means that before 0, which means from here, if I went less than 0, it's getting larger and larger, but in the negative region. The negative gradient gets larger and larger until it gets infinitely undefined eventually at negative 90 degrees. Then that means they said, well, why don't you just draw this part then? Gets infinitely large until you get to negative pi on 2. So they prefer to draw this as your tan graph. Okay, I know we're used to doing 0 to 2 pi, but when you go into exercise 14L, you'll see that they'll draw this as your cycle. It's because it looks nicer. It's one nice cycle. Negative infinity, so you're starting from this side, negative infinity, all the way to positive infinity. Yes?
If the graph has a lot of infinite asymptotes, how do you write the domain?
If it has infinite asymptotes, how do you write the domain?
Yeah.
The domain doesn't change in the sense that it's still from 0 to wherever it is, but between it, the y values are undefined.
Like just if there's no given domain.
Oh, there's no given domain.
Like what's the domain of a y equals 10x?
There is no domain. They're infinite cycles. So like sine and cosine, if you don't put a domain on it.
Would you have to write excluding pi on 2 and minus pi on 2 and 3 pi on 2? Like it's on?
No, you don't have to. Yeah. And but I see what you mean. So if they ask for a domain, I see what you mean. So if they just wrote y equals tan of x, and then they asked you to state the domain, then you would say that it's undefined at pi and 2 and whatnot. But then that's probably where maybe if that question did come up, which I haven't seen before, but if it does come up, that's where you'd summarize it using this formula here. Okay, so this formula here, if we had to dissect it, this is every odd number. 2 times k makes it even, plus 1 makes it an odd number. Pi on 2, which is your every asymptote, because remember 90 degrees, it's always the pi on 2, 3 pi on 2, 5 pi on 2, 7 pi on 2s, and the n there is the dilation factor. Okay, so that's me breaking it down if you really want to understand what the formula is. Otherwise, that's your formula to find the asymptotes. And what's the asymptotes? Right now you've got negative pi on 2 and pi on 2. Okay, so what I'm going to teach you today is simply just that two facts there. You only notice how many x-intercepts you have? 1. How many asymptotes you have? 2. What's the distance or the period between them? Pi. Negative pi on 2 to pi on 2 is a distance of pi. This is all you need in order to sketch any tan graph, whether it's up, down, left, or right. Okay, so watch. I'm going to show you using this theory. This is all we needed to know, right? So here we go. Let's do a typical tan graph to sketch. So let's do this one. Example 26. Doesn't have any ups or downs. If I were to sketch this, this is how easy it is compared to sine and cosine. You've got 3. Remember, the tan graph doesn't have a maximum. The maximum is infinite. So there's no such thing as amplitude. Okay, so don't ever write amplitude equals 3. It's not true. Tan doesn't have a maximum or a minimum. Okay, so the 3 is just simply a dilation. Can't sketch that. We don't know how to sketch that. But we do know we've got a tan graph and n equals 2. Now if n equals 2, the only thing that changes is the period is now pi over 2. So it means the cycle, in order to draw one cycle, it is now a distance of pi and 2 rather than pi. So if I were to sketch this, this is how easy it is. You would draw your axes. Here's my y. Here's my x-axis. Doesn't move left, doesn't move right, doesn't move up, doesn't move down. So if I were to sketch this straight off the bat, here we go. I know that it has to have 2 asymptotes. Now I may not know what the asymptotes is, but I don't need to use the formula. All you needed was the period. This is the period, right? You told me, well, we just figured out the period was pi and 2. Now if it has to be symmetrical, if this had to be half, the distance from here is half, how much is each one? Pi and 4. It's half of half. Yeah, because if the whole distance is half, then to get the middle, it must be half of the half. Half of half is a quarter. So I know this already is at negative pi and 4. This is pi and 4. See, I didn't use any formula, I just used logic. I said, well, if I know the period is pi and 2, I know right at the center, I just got to halve it. So half of pi and 2 is pi and 4, so I know it's pi and 4 on one distance and pi and 4 on the other distance. And then now, if you want to find every other asymptote, how far is it to get to this one? Well, I know from negative pi and 4 to get to pi and 4, how much am I adding on? Negative pi and 4, how much more do I need to get to pi and 4? Yeah, you add the pi and 2. You add the period or 2 pi and 4. I'm only adding an extra 2. Negative 1 plus an extra 2 gives me 1. So that means the next one must be, add an extra 2, 3 pi and 4. The next one must be 5 pi and 4. The next one must be 7 pi and 4. Now once you do that, this is the beauty. How do you sketch a tan graph? We already knew it looks like this. There you go. Well, that was a terrible graph, but there you go. One graph done. Next one. One graph done. Next one. See, it's very easy. There's no top, middle, the whole fine quarter cycles. You don't need that because you know what the shape of a tan graph looks like already. The only thing I'm missing right now is the x-intercepts, but even the x-intercepts are easy. Why? Because every point is a distance of the period. From here to here is a distance of a period. The period is pi and 2. So this here is always 0 because I haven't moved it left or right or up or down. That point there is 0. To get to the next point, you're adding on the period. Pi and 2, so I already know that's pi and 2. So adding to the next one must be another pi and 2. That's pi. And then I just keep going. So I haven't done anything. Notice I haven't used any formulas besides the fact that I'm just interpreting the graph. So if I were to sketch this, I already knew this is now pi on 2. Wow, one cycle done. Next one. I knew that another pi on 2 would give me pi. And the domain said you only go up to pi. So really, if I drew the graph, I can't have anything more than this point. So I must stop here. So that means it must go from negative infinity up until 0. And here's my graph. I've got that side done. I don't need this. This is gone. I don't need that anymore. And that was 0 to pi. And you can follow the same pattern again to then figure out all the other asymptotes. So the next one, minus 2 in that direction. So that's now minus 3 on 3 pi on 4. And then if I continue that, the next cycle must be then negative 5 pi on 4 minus another 2. It's now negative 7 pi on 4. I can keep doing that same cycle over and over and just keep going. Here we go. That's one. That's another one. That's another one. But how many do I need? I only need to go from negative pi to pi. So again, if we followed it, this must be then negative pi on 2 for the period. And then that means this is negative pi. So my answer must be like this. And I've done this, not finding any x-intercepts, no equations, nothing. I literally just sketched the graph simply based on one theory. I just knew what the graph looked like because of a unit circle, and I interpreted what I had. All I interpreted was the period. And just from the period, I was able to find x-intercepts. I knew there was 0. That must be add pi on 2, add pi on 2. Minus pi on 2, minus pi on 2. Same thing with the asymptotes. Period is pi on 2, I halved it. And I've done the first one. So this is why tan graphs is so much easier compared to sine and cosine. No one should be struggling with tan graphs. But what's interesting is that when I give this a sack, I promise you, a lot of people will skip out on tan graphs. And I'll tell you why that happens. It's because they're still spending time working on 14E, 14G, 14H, and they never get up to 14L. So they're like, oh, I can't do it. It's too hard. But is it? No. This is so much easier than 14G or 14H. Should be able to do it. Everyone should be able to do a tan graph without any problems. It's just whether you get up to that point or not. Okay? Dylan.
There'll be like translations.
Yeah, there'll be translation. I don't know if they do horizontal ones. Let's see. What do they do down here? They only do vertical translations. So, year 12, you might get horizontal, but it's the same thing. Even horizontal is still easy because you always have a point of reference was 0. If it moves to the right, add it, and then add on the period. It's not hard to find the intercepts once you know the first one. That's why tan graphs are one of the easiest ones. It's only sine and cosine that you have to spend a lot of time. So if I were to do this one with you, same thing. I'm going to use exactly the same properties, no formulas. I simply look at it and say, all right, period, same thing again. Period is equal to 2 pi, oh sorry, not 2 pi, it was pi. Pi on 2. Again, if I were to sketch it, it only moves up and down. So right now, asymptote means that it doesn't change. So I know the asymptote still is pi on 2, sorry, pi on 4, negative pi on 4 to pi on 4. There we go. But the graph shifts up by 1. So here we go, this is my graph. Shifts up by 1. So instead of 0, it's now 0, 1. So all my graphs, when I draw them, there's a 0, 1 here.